Stars originate from expansive clouds of gas and dust in space. Gravity causes these interstellar clouds to collapse inward. As the cloud collapses, a protostar forms at the center. The protostar continues to accrete mass, eventually igniting nuclear fusion and becoming a star. As a protostar accumulates mass, its core temperature and density increase. Nuclear fusion initiates when the protostar's core reaches a critical temperature and density threshold. Nuclear fusion involves the conversion of hydrogen into helium. This fusion process releases immense energy, marking the birth of a star. The energy released during fusion creates outward pressure that balances the inward pull of gravity. This equilibrium sustains the star's luminosity and stability over its main sequence lifetime. Stars are classified based on their spectral characteristics. O-type stars are hot and blue. M-type stars are cool and red. Spectral types range from O to M, representing a temperature gradient. Stars exhibit significant size variations, ranging from giant stars to dwarf stars. Giant stars can be hundreds of times larger than our Sun. Dwarf stars can be smaller than Earth. Stellar size is a key factor in determining a star's lifespan and luminosity. The classification of stars by size helps astronomers understand stellar evolution. Extreme differences in stellar size influence the gravitational effects and surrounding space environment. A star's color is directly related to its surface temperature. Hotter stars emit light that appears blue. Cooler stars emit light that appears red. This relationship is explained by blackbody radiation. Blackbody radiation describes the spectrum of light emitted by an object based on its temperature. Stars spend most of their lives on the main sequence. During the main sequence phase, stars fuse hydrogen into helium in their cores. The fusion process in the core generates energy that sustains the star's luminosity and temperature. A star's position on the main sequence is determined by its mass and chemical composition. More massive stars are hotter and more luminous, residing at the upper end of the main sequence. Less massive stars are cooler and fainter, located at the lower end of the main sequence. A star transitions into a red giant phase upon exhausting the hydrogen fuel in its core. During the red giant phase, hydrogen fusion continues in a shell surrounding the inert core. The expansion into a red giant results in a significant increase in the star's size and luminosity. The core's contraction and the outer layer's expansion define the red giant's structure. The red giant phase is a relatively short but crucial stage in a star's life cycle. A star ejects its outer layers after the red giant phase. The ejected material forms a planetary nebula. Planetary nebulae exhibit diverse and beautiful shapes. The central star of a planetary nebula is typically a white dwarf. Planetary nebulae enrich the interstellar medium with heavy elements. After the star has exhausted its fuel, the remaining core transforms into a white dwarf. A white dwarf slowly cools down over billions of years, radiating its remaining thermal energy into space. As the white dwarf cools, its luminosity decreases, causing it to fade from view. The cooling process of a white dwarf is exceptionally slow, spanning billions of years. The eventual fate of a white dwarf is to become a black dwarf, a cold, dark stellar remnant. This cooling and fading process represents the final stage in the life cycle of certain stars. Massive stars conclude their life cycles in a supernova explosion. A supernova is a stellar explosion that briefly outshines an entire galaxy. The supernova explosion marks the dramatic death of a massive star. Supernovae are among the most powerful events in the universe. The intense brightness of a supernova makes it visible across vast cosmic distances. A neutron star is formed from the collapsed core of a massive star after a supernova. Neutron stars are incredibly dense, composed primarily of neutrons. The density of a neutron star is so extreme that a sugar cube-sized amount would weigh billions of tons on Earth. Neutron stars possess extremely strong magnetic fields. Some neutron stars, known as pulsars, emit beams of electromagnetic radiation. These beams of radiation can be detected as regular pulses, hence the name pulsar. Black holes form from the gravitational collapse of extremely massive stars. A black hole is a region of space-time exhibiting such strong gravitational effects that nothing, not even particles and electromagnetic radiation such as light, can escape from inside it. The boundary of this region, from which no escape is possible, is called the event horizon. The singularity is the central point of a black hole, where matter is compressed to infinite density. Due to their immense gravity, black holes warp the space-time around them. Nothing, including light, can escape a black hole once it crosses the event horizon. The North Star, also known as Polaris, is a crucial navigational tool. Polaris is located almost directly above the Earth's North Pole. Its position makes Polaris a reliable reference point for determining direction. Navigators throughout history have used Polaris to maintain accurate bearings. The North Star can be located using the Big Dipper constellation as a guide. Following the pointer stars of the Big Dipper leads directly to Polaris. Polaris, the North Star, remains fixed in the northern sky. The Big Dipper's pointer stars serve as a reliable navigational tool for finding north. Using the Big Dipper, one can easily identify the direction of true north by locating Polaris. The North Star has been used for centuries by sailors in the Northern Hemisphere. Sailors use the North Star to determine direction. The North Star can also be used to determine latitude in the Northern Hemisphere. The angle between the horizon and the North Star equals the observer's latitude. By observing the North Star, sailors could navigate accurately even without modern instruments. The precession of the Earth's axis causes the apparent position of stars to shift over long periods. Due to precession, different stars will serve as the North Star at different times in the distant future. Precession is a gradual change in the orientation of Earth's axis of rotation. The phenomenon of precession is known as the precession of the equinoxes.